Alright, so we're working together on the data in the Excel file that I gave you, where we're comparing lengths of axolotls exposed to various teratogens. So again, this is lengths, this is a continuous data. We already found that our data has variances that are close enough, right? So basically we've been working on this tab here, and we even got our ANOVA value already. And so that ANOVA value gave us a p-value well under 0.05. So we know that we have at least one group from this set of data that's statistically significantly different from the rest. Right? So now, what we really want to know is which group is different from the rest. And so in order to do that, we need to do a Tukey's pairwise test. This is the most conservative way to start doing our pairwise analysis. Remember, I already talked about why you can't use a t-test pairwise for all these different groups, because you are not incorporating all of the data at once. Well, with an ANOVA followed by Tukey's, now you can make those pairwise tests that is accounting for all of the total variance in the whole population, all the different groups that the ANOVA gave us. Right? So this gives us the fewest type 1 errors. Again, we want to be pretty careful. We don't want to have a type 1 error where we've rejected the null hypothesis, but the reality was that it's true. And remember, if we do this with t-tests, we have a much higher chance of having a type 1 error, because by the time you've done 20 different measurements, by the time you've done 20 different comparisons of groups together, you're going to, by statistics, just see one of those randomly say that you should reject the null hypothesis even though you shouldn't. Right? So by using an ANOVA followed by Tukey's, we reduce the number of type 1 errors. What we're going to do is create a cutoff saying that with all of this group, we need a minimum difference between the values of x. So maybe we need a minimum difference of values between the means of 2. So what that's saying is, with all the variance here, with everything taken into account, if you have the differences between two means that are less than 2, like 1.6, that's still within range of random variation. However, if our cutoff ends up being 2, and we have a difference between two groups, the means of two groups of 2.5, then that's above that cutoff, and we say that's different enough to be considered statistically significant in terms of that difference. So that's what we're going to work with here. We are going to calculate the differences in means between all of our different groups, and we are going to see if they fall above or below that cutoff for the minimum difference required to call it statistically significant. So, in order to create that minimum difference between two means to call it significant, we need to create our Tcritical. Right? The t-value is the difference between each pair of means, so the absolute difference. So if I have a mean of 8 and a mean of 6, my t-value between those two groups is 2, 8 minus 6. Right? So the t-values simply are just calculating one group's mean minus the other group's mean, and for all the different pairs. But the Tcritical gets a little bit more complex, and this uses the information we have from our ANOVA to calculate that minimum difference to call it significant. So the Tcritical is equal to Q times the square root of ms within over ns. And here are all the different values you will need for this. The ns is the number of observations minimum per category. So in other words, if each of our groups has 8 observations, our ns is 8. That's the replicates, number of replicates per group. A, again, is the number of categories. So if we have 8 different groups, our categories are going to be A. Right? If we have ms within from the ANOVA table, ms within, when we get to the ANOVA table, is shown in this cell right here, and I'll show you that in the ANOVA itself. V is going to be needed. That's degrees of freedom within. So here we see df within, degrees of freedom within. That's going to be 86 for this group. And then Q is going to be a value from this table that we'll come back to in a bit. All right? But you can see that in order to get this value, in order to get the Q value from this table, we need to know A, the number of categories, and V, that degrees of freedom within. So let's take a look at this on the Excel file. So let's go back to our Excel file and look for these things. So remember, NS is the minimum number of replicates amongst our groups. So we can see here that some of my groups have 13 replicates, but the minimum is 11. All right, so NS in this case is going to be 11 because I have a minimum of 11 replicates. Right? A, remember, is the number of groups that I have. Number of categories is what it's scientifically called. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 categories along the way. MS within, remember, we get from our ANOVA table. So this is the ANOVA table we got when we were trying to get that p-value. So if I take a look at my ANOVA table, I have MS within. So my MS within is going to be that value right there. V is my degrees of freedom within groups. So again, we go to this table. There's my degrees of freedom within groups. So V is going to be that number right there. You can always find that in that value of the table. Right? So obviously these values are going to be different for whatever set of data you have, but you're going to get that MS within and the V from this table. All right, so now we need to get Q. And in order to do that, we need to go back to our table from the slides. And in order to get Q, I need to remember what A is. Our number of categories is 8, and I need to remember our V, degrees of freedom within, is 86. All right, so let's go back to our slides. Here's our table. Remember, A was 8. That's our degrees of freedom here. And V was 86. Well, at the end of this table, I'm not close to that, but luckily on the next slide, we kind of have this extending further. And V is 86, we are always going to round down. And here's how I know this. Right? I am always trying to get the more stringent value here. So if we have degrees of freedom 8 and we're rounding down to 60, even if kind of understanding the stringent value at this point doesn't make sense, don't worry about it. You're rounding down here because that is the more conservative way to do this. Right, so just remember to round down. So 86 rounds down to 60. Even if we had 115, we still would go down. Right? So my Q value ends up being 4.44. 8, 86, rounded down. So 4.44 is our Q value. Let's head back to our Excel file here. We can even just put that in. That was 4.44. And now I can use that to calculate my Tcritical. So I can go equals, and I know I need 4.44 for the Q, and I need times, and then I need my square root function, which we've used before, times the square root of, and then MS within, divided by NS. And I forgot to close the parentheses, but it's correcting that for me here. And so there is my Tcritical is 3.49, essentially. All right, so I can take this and I can get it to some significant digits, drop it down, 3.49. What does this mean? Well, this means that I have a minimum difference between my groups of 3.49 to call it significant. So if I look at these two means here, right? So remember, these are lengths of axolotls. This one's been exposed to 10 micromolar cyclopamine, this one to 100 micromolar cyclopamine. These are the mean lengths. So I'm going to have a difference of nearly 0.6 here. But that is not nearly enough to be considered a significant difference with all of this data, the variation in mind. So those two groups would not be significant. However, maybe I look over here, I see 5 and I see 9. The difference between those two groups would be 4. And a difference in 4 is above my minimum cutoff to be called significant. So these two groups would be significant. This is what this is telling me. This is helping me identify that in this case, the 10 micromolar retinoic acid group must be significant from the D-jelly control group. Right? But really, in order to do this, we want to set up a table so that we're making every comparison. So this table here, all I've done is I've taken the averages from all of my groups here, and I've put them on two different columns and column and rows here. That way I can take each one and I can subtract this minus this, this minus this, and each of these values is comparing two different groups. So for example, this value right here is comparing the 1 micromolar retinoic acid to this. And you don't have to worry about the negatives. Remember, it's the absolute difference. So this would still be just a difference of 3.33. In other words, all three of these, negative 3.83, negative 4, negative 3.83, I've highlighted them because those are the ones that are significantly different. My value here came above the minimum Tcritical. My values here, sorry, came above the minimum Tcritical. Therefore, these are significantly different. So I can say that the 10 micromolar retinoic acid is significantly different from the no D-jelly control. The 10 micromolar retinoic acid is significantly different from the D-jelly control, and that group, 10 micromolar retinoic acid, is significantly different from DMSO control. The negatives tell me which direction. So since I subtracted this minus this, it's just negative because this happens to be smaller. So I can take that a step further and say the 10 micromolar retinoic acid group is significantly shorter than the D-jelly control group, and so forth. So now what I want to show you is how I created this table. So I'm just going to create this table right underneath it so you can see what I'm doing. And one of the things you'll want to know how to do is basically create, use the dollar signs. I have another video in a Canvas that helps you how to do that. So I am going to copy my labels here, and I'm going to create that set of labels over here. And then I can take those, because I want the same groups on the y-axis, so I can copy them. And there's this cool little function in the paste. So I can go to paste special, and transpose is what I'm going to want. So I need to click down here. I'm going to come back to it in a sec. I need to give myself room for the two sets of data, so I'm going to put it here, put it right there, sorry. And I am going to paste special, and if I hit transpose, everything that I've done in this axis will now go in the columns, right? And now I want the values so I can subtract them. So I want these values here. But remember, if I just copy this, these were all functions. This was an average. You can see it up here. This is the average of the groups above it. So if I just paste that here, it's going to be looking for the averages of the groups above it. So I need to not just hit copy and paste. Again, I'll go to my paste special, because this time I want to paste the values. Normally it pastes the formulas and is looking for new data above it. But I want to paste the values. So there's my values. All right, and I can put that into a manageable kind of looking set of decimal points. Put these up here. And then I can copy that, and remember transpose? Well, I'm going to use that again. I'm just going to transpose that same data because my no D-jelly control has 8.9. Here it also should have 8.9. So I'm going to go to my paste special, transpose again, and boom, there's my data. Now, in order to compare all of these, I could simply just go equals that minus that. That's the comparison of those two cells, and that's obviously going to be 0 because here I'm just comparing no D-jelly to no D-jelly. It's the same group, so there's not going to be a difference. But I could do that for every one of these and take my time. Or I could do that and paste this around the way, but let's just look at this here. This then, everything is moving over with it. So this was that minus that, but if I just copy it, this is now moved over there, but it's minus that. And all of these values are going to be wrong. So what I have to do instead, if I want to do this individually, in this case, I want this value to move. I want that value to move over with it. So I'm going to leave that one alone. But I want this value to stay the same. So if I put dollar signs, that means column C should stay the same, and number 40 should stay the same. So if I have dollar signs aside both of that, then that's going to stay the same, and now I can copy and paste that across. Right? And you can see here that over here, this is now age 39. That has moved just like I wanted it to, but it still is comparing to this one, C40, because I put those dollar signs. Now, I could be even a little more strategic here. So I could say that I know that for all of these, I want the row here to stay the same. I want the column to move over, but I want the row to stay the same because as I move over, the column's changing, but the row, 39, should not. Don't want it to drop down with it. And this guy here, I actually want the opposite. I want the column to stay the same. I want the column to stay the same, but I want the row to change as I go. And if I do that correctly, I can now copy and paste everything over. and you can see that along the way, everything stayed the same. This is still that H39 minus this C41.